So this circuit is switched on at t is equal to 0. Here is the circuit, LR circuit, a standard LR circuit. And let I be the final steady state current. As we know that in case of LR circuit, the moment the switch is connected, at that time current remains 0. Because at time t equal to 0, inductor behave like infinite resistance, I've already told you. And at t equal to infinity, it behaves like a zero resistance. In case of ideal inductor, of course, it behaves like zero resistance at t is equal to infinity. And as far as the current growth is concerned, it is given by this formula, I is equal to I naught 1 minus e raised to the power minus t by tau, where tau is time constant and it is equal to L by R. Here I naught is the steady state current. Suppose here this particular battery has got the EMF E. In that case, the final steady state current I naught is going to be E divided by R, because we know that at time t is equal to infinity, after a long time, this particular inductor will start behaving like a zero resistance. At that time, circuit current would become E by R. That you can see it clearly. If this is having zero resistance, then current must be E by R only. Okay, so let's move towards the options available. So here one thing, you can see that I is the final steady state current. Okay, capital I. So here I naught is basically this capital I. So let it be capital I here also. Okay, and small I is the instantaneous current. So capital I is the steady state current. So voltage across R is Ri after a long time. If I is the current, steady state current, then after a long time voltage across this resistance will be IR. And in fact, that will also be equal to the E. Here in this question, which of the following given statements is not correct? We have to find which of these following statements is not correct. So first let's select which of these statements are correct. So voltage across R is Ri after a long time. So this statement has to be correct anyway, because IR is the potential difference across the resistance. After a long time, energy stored in inductor becomes constant. And so in this case, work done by the battery is dissipated in the form of heat completely. Yes, that's true. As we know that after a long time, the circuit will attain a maximum steady current I, which is E by R. At that time, whatever energy is stored in the inductor, that will remain there, and whatever work is done by the battery to drive this current in the circuit gets dissipated in the form of heat across this resistance. But initially, when the switch is kept on, then initially the current start growing. So what happens? Some part of energy gets stored in the inductor and some part gets dissipated, and but as soon as the steady state is achieved, in that case the current becomes steady, so I, and potential difference across L becomes 0. Okay, so voltage across R is Ri after a long time. This is correct, and this option is also correct. After a long time, energy stored in inductor becomes constant, that I have told you. And so in this case, work done by the battery is dissipated in the form of heat completely, obviously. See, voltage across L is equal to 0 at t equal to 0. So voltage across L, initially, as you can see that at time t is equal to 0, inductor behaves like infinite resistance, so there won't be any current in the circuit. So whatever EMF is applied, the same must be the potential difference across this inductor. So it is not equal to 0. Alright, so this statement is basically voltage across L is equal to 0 at time t is equal to 0. So this is wrong statement. Magnetic field energy stored after a long time is half Li square. That's correct. So these three options are correct. One is wrong. So which of the following given statements is not correct? So our answer has to be C only. Have you got the point? We have to select the incorrect options. You have to be extra careful in such questions.